Hi, I'm Jeff, one of the instructors in Medlytics. In Medlytics, short for Medical Analytics, we teach students to apply machine learning approaches to real medical problems, including predicting patient hypothyroidism, classifying sleep states from physiological signals, and identifying cancer in mammography images. Using these problems, we can motivate and demonstrate a gamut of machine learning approaches, including decision trees, support vector machines, and convolutional neural networks. Let's take a look at some of this year's student presentations.
And welcome to the live session for this year's Medlytics course. Our students have worked tirelessly over the past 4 weeks to learn and apply machine learning techniques to new medical problems. So we are excited for you to see their final products today. This course was designed to introduce students to the intersection of medicine and data analytics, hence the name Medlytics. The first 3 weeks of the program were focused on introducing students to new data analysis and machine learning techniques. The first several days of each of those weeks were spent teaching the students a new set of concepts to address to their, or use to add to their ever-growing analysis tool belt. For the second half of these weeks, the students would break up into small groups to collaborate on a challenge problem. And these problems were selected to really force the students to make use of their newly acquired skills.
Thanks, Jordan. So as Jordan was saying, this summer in Medlytics, we've guided the students through 3 machine learning challenges to test and grow their understanding of the field en route to these BWSI final projects. In week 1, the course introduced decision trees, support vector machines, and logistic regression classification. Using these techniques, students were then asked to create a high accuracy algorithm to predict patient hypothyroidism based on available medical data. Next, in week 2, we turned to focus on analysis of signals and classification of those signals. Students explored feature extraction techniques on raw recorded signals that included manual feature extraction and neural networks. Week 2's final project then challenged students to properly classify sleep states in patients using only a handful of recorded physiological signals.
For the third week of Medlytics, our students were introduced to the world of computer vision and convolutional neural networks. By leveraging multiple classification techniques, our students were able to apply and build a set of computer programs that could accurately classify various states of cancer within a database of mammography images. Having completed all of those challenge projects for our final week of the 2020 BWSI program, the Medlytics students were set loose to identify and tackle a project of their own. This involved scouring the internet for example problems to solve and identifying which data sets might be available to help them solve those problems. The students then had to identify an individualized approach to each of their projects with minimal help from teaching staff, and then build a tool to analyze and provide valuable medical insight into their selected problem. These are the final projects which we'll be presenting to you today. They represent many late nights of work and many early mornings logging onto our servers to continue collaborating with their colleagues. And with that, we'll hand it over to our first group, FatiQue and Slept. So a collaborator within that group, if you'd like to unmute yourself and start sharing your screen. Fantastic.
All right, can everybody see?
It looks good,
All
Andrew.
Right. Thank you. All right, so we're FatiQue and Slept, and today we'll be presenting on melanoma classification.
I'm Advika Santi.
I'm Andrew Zhao.
I'm Clarice Liu.
I'm Simon Traub.
And I'm Xiang Huang.
So every year, more than 1 million Americans are diagnosed with skin cancer, making it the most common type of cancer. Our focus is on one type of skin cancer called melanoma. Melanoma occurs when melanocytes, which are melanin-producing cells, multiply and grow uncontrollably and form a tumor in the victim. Despite being less than 1% of skin cancer diagnoses, melanoma causes 75% of all skin cancer-related deaths. Often, the first sign of melanoma is a change in the shape, color, size, or texture of an existing mole. However, a new melanoma mole can develop anywhere on the body, making detection very difficult for doctors. Luckily, it can be cured with a minor surgery if it is caught early enough. So the earlier it is detected, the higher the chance of survival will be for that patient.
And consequently, our goal is to improve in these early skin cancer diagnosis to improve patient outcomes. Now, we do this through a process called machine learning, which means that we train a computer to recognize images based on a training set and then extrapolate to generalized data sets.
So we will now be discussing exactly what we did for our solution to this problem. So the very first thing we had to do was select our data. So there were two main types of data that we could choose from. The first one was patient-level contextual information, which is essentially just general information about the patients from which the samples were taken from. The second type of data was binary classified RGB images. What this is essentially colored images that are classified into two categories. The two categories are either malignant, meaning that the patient that the sample was taken from is diagnosed with melanoma, or they were benign, meaning that the patient that the sample was taken from is not diagnosed with melanoma. So we exclusively chose to go with the images and not the contextual information. So after downloading our data, we had to strategically divide it into categories. This was called our data splitting. So training data is what the model learns from. Every photo is analyzed to help the algorithm find patterns. The more images that are used, the more accurate the algorithm will be. This is why it is crucial that the majority of our data is used for training. The training group is necessary for the algorithm to learn the different patterns. Validation is the intermediate checker. After training the model with the training data, we run the validation set through our model to find its accuracy against the new data presented by the validation set. We want this group of our data to be relatively small, otherwise our model might over-accommodate the validation data. The testing data set is our final group. This is run at the very end to gauge how our model would perform in real life. If the model persists its high accuracy, it's good to go. Otherwise, more modifications will need to be made to the model before it's integrated for real-world medical purposes. The numbers in the slide simply indicate how many data points were used for each group.
Yeah, so our next step was to normalize the data. Now, what this means is just making the data more comprehensible to the machine, essentially easier for it to process. Now, the biggest challenge that we ran into was that 90% of the downloaded data set were benign cases. And the problem that presents is that our model could simply learn to say false every single time, say that the patient is benign, when in reality, you'd be missing 2% in the training set. But also, if you generalize to broader terms, not every data set's gonna have 98%. What happens if, only 1% is benign? Then we've made a really big error. So to combat this, we downloaded supplemental malignant images from previous competition to normalize and oversample. And what this really means is we're just teaching the machine to recognize these malignant images when they actually do have melanoma and correctly diagnose them. So that way, when we generalize to a data set that isn't our training set, per se the validation, the test, or just in general, it will actually generalize and diagnose correctly. Now, another thing that we did was augment the data, and that also helps with combating overfitting. That's because it minimally alters existing photos to produce quote unquote new data points. So for example, you might change the image hue in the data or in a picture, or you might rotate it. Simply that way it helps with generalization.
So our project consisted of two models. The first model was based on two machine learning techniques, neural networks and transfer learning.
And so you may be wondering, how does a neural network work and what is it? So essentially, neural networks are an algorithm for computers designed to mimic the human brain. Neurons take an input, kind of generate new insights into it, and then pass it on to another neuron with the end goal of producing some output. So for example, if we look in the example, we look at a picture of a boat. Now it passes through multiple layers, each that has neurons inside of it, to essentially gain new insights and really determine that, it's not a dog, it's not a cat, it's actually a boat. And that's exactly what we're doing. We're training our machine to learn how to recognize objects and images.
We used a technique called transfer learning to build our model. The technique utilizes a pre-trained neural network that is effective at classifying general images and then slightly adjusted to interpret medical images. In our case, we used two very reputable networks known as EfficientNet v2 and Inception v3. These were pre-trained to perform general image analysis and are verified by AI experts. Then, after loading in these neural nets, we added two extra layers at the end to interpret the results in a medical context. When we train the model, there are some parameters that we can choose to enhance the learning process. We want to emphasize the following 5. First, we chose to use 20 epochs, which means that we ran the model through the full data 20 times, ensuring it had enough time to learn. By randomly shuffling the data, we evenly distribute the benign and malignant cases among the data set. Through adjusting weights We bias the model to prioritize malignant images, countering the disproportionately abundant benign samples in our data set. Next, we unfreeze layers in the neural network. In practice, this just means that the model could more effectively learn to specialize in medical images. Finally, we utilize early stopping, halting the model when its accuracy starts to decrease, meaning we can not only shorten the runtime, but also take advantage of the model when it's around peak performance.
What you're seeing here are confusion matrices. They help us check out just how functional our neural network is in practice. Even if our model has a high accuracy, it's important for us to check that images are being classified into the correct category. In this type of diagram, we want the top left and bottom right corners to be the darkest. This indicates that our neural network is accurately diagnosing malignant moles as cancerous and benign moles as harmless. That's why our initial matrix is problematic. As shown in the top right corner, there are too many cancerous moles being diagnosed as benign. On the contrary, we see that our final and improved model effectively predicts both benign and malignant cases, making it a great tool for diagnosis.
So the majority of our week was spent experimenting with transfer learning, but we wanted to find a method that even further increases our accuracy. To do that, we need to answer two key problems. First of all, how can we make our data more evenly distributed? And second of all, what model will do that? So that's why we went with EfficientNet B2 with K-folds as our second model, going above and beyond to research new concepts we weren't taught in class. What a K-fold model does specifically is retraining the model K times using the entire data set, separating a different portion of the data each time as a test set. So for example, the image here on your right shows K is equal to 5. Each horizontal block represents a fold or equally sized group. In this case, our entire data set is being divided into 5 folds. The algorithm then moves down diagonally, taking a different section of the training data to set aside as the test data. This just makes our data more distributed overall. We also use EfficientNet models, which is a family of neural nets that are tailored to perform fast image analysis. Their speed allows us to build a more complex and accurate neural network. Since the network is being retrained K times, we have to run through less of the data set through each iteration. This is important since it cuts down on the time to train the model. We continued modifying our project by adding more layers, changing parameters, and so on until we settled on 5 folds, which was sufficient to return a high accuracy of 99%.
So, what's next? First, we want to acknowledge that our current model and training procedures are not perfect. We can continue to try tweaking the parameters, or even employ another transfer learning model to shoot for better results. We're planning on submitting our model to an online competition run by Kaggle, a medical database that was used for research by other groups in Medlytics. Thousands of data scientists are competing worldwide. Kaggle uses a special metric on a scale of 0 to 100 to evaluate a model's performance. Our model is hovering around a score of 94, while some of the best models top out at a score of 96. Our goal is to bridge that 2-point gap and to submit our model to bring in the dough. Our group is very passionate about machine learning and are excited to push our project to the next level. So thank you so much for watching our presentation. We hope you enjoyed and learned something new with us. At this time, we would also like to give a special shout out to our amazing instructors and TAs. If it weren't for their unwavering dedication and generosity, we wouldn't have learned and grown nearly as much as we did. If you have any questions, we're happy to do our best to answer.
Fantastic. Thank you very much, FatiQue and Slept. We are actually going to be handling questions in maybe a bit of an unconventional way. Feel free to be populating the chat down below your webinar view window. There should be an area where you can put questions in. And what we're going to do is at the very end of all the presentations, we'll have a period where we can pose questions to each of the groups that's gone. And maybe there will be some commonalities that different groups want to address together. But please, by all means, submit your questions. But for now, we are going to move on to the next group on our list, which is Rona Group 1. If someone would like to unmute and start sharing their screen. Fantastic.
All right, so we are Rona Group 1. I'm Alice Wu.
I'm Rachel.
I'm Tally.
I'm Tiffany.
And I'm Avery. So for our project, we created a model to predict the outcomes of COVID-19 patients. As mentioned in our video, many hospitals are running low on capacity and running low on supplies as well, such as hospital beds and ventilators. And the primary problem is that these supplies are assigned reactively rather than proactively. So today, we'll be using machine learning in order to give the doctors a better idea of the amount of supplies and space they need so they can prepare in advance.
So what is being done now? Doctors are treating symptoms as they arise. Resources are allocated in response to patients needing them, and hospitals and ICUs are close to full capacity. Our goal with this model is to 1. Allow doctors to prepare treatments and equipments in advance, such as ventilators if a patient needs to be intubated and ICU beds for patients. And 2. To classify a patient's risk factor based on their pre-existing health conditions. Our risk factors are intubation, being put in the ICU, or if a patient is at risk of death.
So for our data set, we used anonymized COVID-19 patient data from the Mexican government. This data set contains information on pre-existing medical conditions. We trained on the positive COVID tests, which left us with about 220,000 data points out of the original 500,000. We split these points into training, test, and validation sets. And then we also performed oversampling because the data was massively imbalanced towards the negative outcome of no complications due to COVID. This was clear to us when testing with the zero rule algorithm, which simply returns the mode of the output feature. We got a 97% accuracy by simply returning negative every time. So by oversampling, we used SMOTE, which stands for Synthetic Minority Oversampling Technique. And basically, it inserts synthetic data into the minority class in order to balance out the ratios. And by doing this, we got back to a normal 50% accuracy.
We also tried a variety of classifiers when creating our model, and then ultimately we decided to go with a random forest classifier. And so this model essentially creates a given number of decision trees with slightly different structures, and then generates the final class based on the majority vote of the decision trees. And so as you can see in the diagram on the top, a decision tree consists of a series of yes or no questions that splits up the data into final classes. Now, sklearn, the Python package we use, automatically generates these random forests for our data. Because our three factors are not mutually exclusive, we created 3 separate models, each fine-tuned at the risk factor.
So what makes a good model? There are a bunch of different ways to evaluate how well a model performs. Here we will explain 2 metrics that we use to evaluate the performance of our model. So AUC stands for area under the curve. To describe what AUC means, consider a model's prediction of the chance for an entry to be in a class to be that entry's score. Then the AUC is the probability that a randomly chose entry that truly is in a specific class will have a higher score than a random entry that is not in that class. An AUC of 1 is perfect, while an AUC of 0.5 means the classifier is no better than random.
The second evaluation metric we used was a confusion matrix. A confusion matrix is a table that shows how many predictions you got correct and how many you got incorrect. The top left corner are their true negatives, that is, all the data points that were correctly identified as negative. In this case, these are all the patients that were correctly classified as not having the risk factor in question. In the same vein, the top right corner are the false positives, and the bottom left corner are the false negatives. These are the patients that were incorrectly classified as having the risk factor and not having the risk factor, respectively. And finally, the bottom right are all the true positives, aka all the patients that were correctly classified as having the risk factor.
So specifically, what did our model look like? First, we're going to discuss the features we chose, which are essentially what factors the model looked at when it was trained. And even though we're looking at multiple features, almost all of the columns in our data set, keep in mind that these are relatively simple questions that are easy for a patient to answer. Each model also returns yes or no for a given label, with the labels being the risk factor in question. For example, the model for intubation will return yes if this patient was intubated, or no, they were not. And like we said earlier, we actually had 3 separate models for each factor, and this meant that for the higher risk factors, we could use the lower risk factors as features. For example, we could use the intubated or ICU labels as features for the 3rd risk factor.
As for parameters are kind of like the fine-tuning knobs of a model. So I'm just going to go through and kind of explain what some of these do. The number of estimators is how many trees are in the forest. Each one is slightly different, and at the end, the majority vote between the outcome of each tree is returned as like the final outcome. The max depth parameter is the maximum amount of decision nodes that a data point can be passed through. The more you have, the more specific the model becomes. But if you make your depth too deep, the model can overfit to the training data, meaning it doesn't generalize well. We actually found that having a deeper max depth for a third risk factor proved to perform better than the max depth of 10 for our lower two risk factors. And then finally, the minimum samples per leaf means that any resulting leaf that classifies less than 5 samples is removed. This is also a parameter that can prevent overfitting. So how did our models do? As you can see here, the models performed quite well. These three tables are called normalized confusion matrices. Because of the class imbalance in the data, regular confusion matrices aren't great at showing how well the model performed. The normalized confusion matrix gives a much better picture of how the models performed because it displays ratios rather than raw data. The top row contains people who are negative for the risk factor, and each box in that row contains the percentage that were classified as that out of the total number of negative people. In the same way, the bottom row contains people who are positive for the risk factor, and each box in that row contains the percentage that were classified as that out of the total number of positive people. A perfect model would have ones in the top left and bottom right, and zeros in the top right and bottom left. And as you can see, all three models had AUCs of 0.85 or higher, which is quite good. And I'm sure that you've noticed, but we didn't actually use accuracy at all due to its unreliability, as the data is very skewed to the negative case. That is, because so many people did not need hospital treatment and did not die, the validation accuracy would have had a very high percentage despite having a bad confusion matrix and AUC score. In short, the model would have spit out a high accuracy no matter what. The AUC score and the normalized confusion matrices are much more representative of the actual quality of the model.
And finally, we'll discuss the uses of our model and how we build on it to improve. It is important to note that the models are not accurate enough to reliably classify a specific patient's outcome. That is, we would not advise doctors to use this model in order to determine the treatment that a specific patient would need. We also do not want to discourage patients from getting treatment in case the model predicts that the specific patient will be fine, when in reality they may actually need treatment. However, hospitals can still use these numbers on a larger scale by using them to prepare the necessary amount of equipment, which was the goal for our model in the first place. In order to improve future models, correlation between pre-existing medical conditions and complications due to coronavirus should be analyzed more to identify which are most representative of the effect of COVID-19 on a certain patient. Furthermore, better results might be acquired through the use of more comprehensive, discrete data that goes into detail about the severity of each pre-existing condition.
That concludes our presentation. Thank you guys for listening. We'd like to give a special shout out to our instructors for teaching us for the past weeks and helping us through our final project, and our TAs for always being there when we needed help debugging our code.
Fantastic. Thank you so much. Again, we're going to be postponing questions until after all of the groups have presented, but if you have a question for Rona Group 1, feel free to submit it through the question interface just below the viewing screen in your webinar session. All right, and with that, we are on to our next group.
Good afternoon. We are the Neuro Bureau, and welcome to our presentation on detecting Alzheimer's disease. Let's start off by defining what Alzheimer's disease is and why early diagnosis is so important. So why are we eager to refine a better diagnostic process for Alzheimer's disease? Alzheimer's disease is currently the most common neurodegenerative disease worldwide, and it results in memory loss and cognitive difficulties. It's estimated that around 50 million people will suffer from it, and that number is supposed to more than double within 30 years. In addition, although there are medications to help with symptoms, there is currently no cure. Therefore, accelerating and refining the diagnosis can save countless patients from irreversible brain deterioration.
So the second step of our project was to develop a solution to solve this problem. Here we have some example MRI brain scans from patients with Alzheimer's disease. We obtained the images from an open access database. In this dataset, images are ordered into 4 classes based on their degrees of dementia, which is a hallmark to show the severity of patients' Alzheimer's disease. As you can see, all 4 stages look kind of similar, and they are difficult to be distinguished by naked human eye. Our approach to solve this problem was by using a convolutional neural network, or CNN. If you recall from our introduction video, and CNN is like a function with filters inside. It will produce an optimal output. Each layer within the CNN can be embedded in something called a layer. And the number of layers in a CNN can range from just a few to several hundred.
The third step of our approach was to test different CNN models. There are already several well-established CNN architectures, so we decided to select a few of them, use them as our baseline, and try to improve them where we could. The different CNN architectures we tried were LINET5, AlexNet, VGG16, and DenseNet. As mentioned before, CNNs consist of several layers. In these graphics, each block or series of squares represents a layer. Some CNN architectures contain more layers than others, such as VGG16, and these tend to be more computationally expensive. One of the CNN models we tried was LINET5, which is a classic CNN architecture. It's a fairly simple architecture as it only has 7 layers. On the left is a summary of the layers and parameters used in the LINET5 model, and on the right are plots showing how the model's loss and accuracy changed over time as it trained and ran on a mock test dataset. The upper figure shows how the loss decreased quickly before maintaining a stable state, and the lower figure shows how the accuracy increased quickly before leveling off. Both of these are characteristic of a good model. Also, on the far right, you can see that the model yielded a 96% accuracy, and the loss, which can be thought of as the sum of its errors, was only 0.308, so LINET5 performed quite well. Pictured in the bottom left is a multi-class ROC curve. A good model should maximize the area under this curve, with 1 being a perfect score. LINET5's AUC ROC, or area under the ROC curve, was 0.991. which is a very good score since it's so close to 1. The figure shown on the right is a multi-class confusion matrix. Each row and column represents a stage of dementia. A confusion matrix can show 2 types of incorrect predictions, false positives and false negatives. An example of false negatives is the 0 in the top right cell with the red circle, which indicates that 0 patients who have moderate dementia were classified as having no dementia. It's fortunate that LINET5 had 0 false negatives for moderate dementia in particular, as it is very dangerous for moderate dementia, the most developed stage, to go undiagnosed.
So another architecture that we tried out was called AlexNet. So to the right are 2 diagrams showing the model's loss and the model's accuracy. And in general, we want to minimize loss and we want to maximize accuracy. So we can see from the model's loss curve that it flattens out at the bottom and the model accuracy curve peaks out, signifying that our model is doing pretty well. So on the left is a multi-class ROC curve for AlexNet. So the ROC curve is a classification metric or a way to see how well our model performs. And the ROC curve does this in a very probabilistic manner. So in an ideal world, the lines are going to shoot straight up and go to the right, just like the red curve, which would maximize the area under the curve like previously mentioned. And on the right, we have another confusion matrix for AlexNet. So rather than being a classification metric in a probabilistic manner, confusion matrices are more numerical in approach. And if we look at the circle 2, so the 2 represents a false positive. So that means 2 patients who did not have dementia were incorrectly labeled as having mild dementia.
So out of all the CNN models we implemented, LINET5 achieved the highest accuracy of 96%, and AlexNet achieved an accuracy of 93% in detecting which stage of Alzheimer's disease a patient was at. The other 2 models we trained did not yield accuracies as high, which is most likely due to the fact that the larger and more complex networks were more memory expensive, particularly VGG16. So we had to train those models with fewer epochs, meaning that we passed the entire data set through the network fewer times, which led to lower training accuracies. So once we saw that our models were achieving high accuracies, we finalized on LINET5 and AlexNet as the 2 models we would focus on. Next, we moved on to implementing them in the real world to help clinicians with a user-friendly web app. On our homepage, we start with an introduction of what exactly Alzheimer's disease is to provide some context on our project. We also break down which parts of the brain are primarily affected by Alzheimer's. Scrolling right along, we then explain the relevance of our project. And finally, at the bottom of the homepage, the user can click a button to go and classify a brain MRI scan. So on the classify page, the user sees a form that simply asks for a brain MRI scan. Right now, we're testing our app with test images from our dataset. After attaching the image and classifying and clicking the classify button, the model runs, and a few seconds later, the results show up on the screen. So we just inputted the MRI scan of a patient with very mild dementia, and as you can see, AlexNet correctly classified it, but Lynette classified this patient as having no dementia. And at the bottom, you can see the breakdown of probabilities across each model. In this case, AlexNet was 68% sure that the patient had very mild dementia, and Lynette was 94% sure that the patient had no sign of dementia. So next we tested this with a scan of a patient with moderate dementia. And we click classify, and after the models are running in the background, the results show up on the screen. So in this case, AlexNet was very confident that the patient had very mild dementia, and Lynette was very confident that the patient had mild dementia. So in this case, both of the models incorrectly classified this patient. However, currently, detection of Alzheimer's becomes more accurate when a patient reaches the moderate stage, which is when the symptoms become more apparent. So although our model performed inaccurately in diagnosing late-stage Alzheimer's, it performed well with early detection, which is crucial in applying intervention to slow down and prevent irreversible brain damage.
So in the future, our goal is to implement more complex convolutional neural networks and explore larger and more comprehensive datasets, such as ones that include patient medical history, demographic group, and other diagnostic test results. As the number of people with Alzheimer's disease is growing, our model is one step towards making early diagnosis more accurate and efficient.
We would like to thank our instructors Jordan, Jeff, and Thomas, as well as our TAs Emily, Ujwal, and Charvel for their help and guidance throughout these past 4 weeks. We look forward to answering any questions you may have during the Q&A segment. Thank you.
Thank you, Neuro Bureau. So again, if you have any questions for the Neuro Bureau about their approach to classifying and detecting Alzheimer's disease, feel free to submit those through the question interface below your view screen in the webinar. But next up, before we have a chance for questions, we're going to look at another presentation, this one from NASA Junior.
Hi, everyone. My name is Alex, and I am a member of the NASA Junior team for Medlytics this year.
I'm Neil.
Dad?
I'm Sam.
And I'm Joanne.
And this is our presentation on how we used machine learning to improve lung cancer detection. Just some quick info on our team is that we've been working together since day one. While groups are randomly assigned for weeks 1 and 2, our group met week 1 and continued to communicate and work together throughout the entire program leading up to this final project. Our objective for our project was to use images of lung tissue to develop a model which could accurately and efficiently diagnose a subject with lung cancer. Here's an image of the data set we use, which consists of 25,000 images of lung tissue and colon tissue, also known as histopathological images. Our team focused only on lung cancer, not colon cancer, which left us with 15,000 images out of the original 25,000. These 15,000 images consisted of 3 categories of images. On the left, you can see a histo image of someone with adenocarcinoma lung cancer. The middle image is of someone without lung cancer or benign, and the right is someone with squamous cell carcinoma.
Since lung cancer is such a common type of cancer, we designed our algorithm to help mitigate the need for a second opinion from another doctor. This would in turn help reduce cost, diagnosis time, and the need for additional risky biopsy tests. Especially during this COVID pandemic, where every available assistance is needed for COVID testing, quicker diagnoses can help those in critical danger due to lung cancer receive their needed attention in even less time. Convolutional neural networks can help us build algorithms that automatically find characteristics in images to differentiate one type of lung cancer from another. First, we input images into our model. From there, we process the data in our network's nodes, and then we receive an output. This output is used to train what is known as a weight. Weights affect the processing of new data, and this is where the learning aspect of machine learning comes into play, as the new weights will be used to train the next layer of nodes.
Unlike traditional machine learning, where we would directly input lung cancer images, we utilize transfer learning in that we trained a convolutional neural network on ImageNet, which is a public database of 14 million images. Then we used the weights generated from the ImageNet trained CNN on our lung cancer model, even before inputting our lung cancer images. Doing this before helps our model learn how to find unique features that can help identify what types of objects are in the images. Finally, we trained our model on the lung cancer images, which was primed with the ImageNet weights to accurately predict lung cancer. So our model is an example of a multi-class classifier. So unlike a binary classifier where we would ask, do we have cancer, yes or no? Instead, we ask, what kind of lung tissue is this? Is it benign adenocarcinoma or squamous cell carcinoma?
So our algorithm development process. First, we read published studies done on the analysis of histopathological images to find techniques they used and how they pre-processed their images for better models. For example, we read a published study that analyzed the histopathological images of neck tissue, which helped us a lot. Then we researched how to train large image data sets. We learned that we had to create a smaller data set to test our models to see if they were any effective before training our real data set, which took hours to run. And then we solved challenges to optimize model accuracy while reducing train time. And then we tested various CNN architectures. Each of us tested various different CNN architectures, and we took the best model, which we all then ran again to collect the final results, and just in case someone's program crashed while running. And finally, we built a web application for the ease of access for healthcare professionals. So what we learned in the process and learned from experimentation and lectures in earlier weeks helped us solve issues that arose in our process mentioned in the previous slide. We had long trained images and frequent out-of-memory errors due to the high resolution images. So we resized our images to 224 by 224 pixels from 768 by 768 pixels using the image data generator function, which we learned just this week. This function also helped us to load our huge files containing thousands of images and helped us perform data augmentation, which is the altering of training images, like rotating them randomly, changing their hues before training the machine learning model. It's used to build more robust machine learning models. And we specifically used the augmentation of zoom through image data generator and zoomed into and out of our images by a range of 20% so that the zoom of the images would account for the resize of the images while training the model and build a more robust model that could account for different histopathological images. We also learned how to implement new transfer learning models from reading their documentation and from how they were implemented in published studies.
So our team attempted to implement several models, such as ResNet 50 and ResNet V2, but one model that outperformed all the rest in terms of accuracy was VGG19. We discovered this network after seeing it was implemented in image processing, such as malaria detection in blood smear images. Our final model was trained using a VGG19 transfer learning network pre-trained on ImageNet, which has around 14 million images. Now, while this might sound complicated, essentially, our model combined convolutional neural networks as well as transfer learning to develop a complex and accurate model.
So our group was fortunate enough to build a successful model pretty early on in the week. And thus, I shifted my focus on to web application to detect lung cancer. So doctors could use this in their offices to easily predict. The basic functionality is it inputs a histopathological image, and our web app classifies it as either lung adenocarcinoma, benign, or squamous cell carcinoma. In order to get a better idea of this, we prepared a live demo for you. So this is our website right here, and you can see its homepage, National Year's Lung Cancer Classifier. We have team members on the left side, our logo right in the middle, as well as the Medlytics course logo on the right side. But the main page is the classify page right over here. And here we can choose a histopathological image. We'll choose one of squamous cell carcinoma. And hitting classify will have our model classify this image and outputs a set of probabilities for each class. So in this case, our model thinks there's 0% chance that it's benign, 0% chance that it's lung adenocarcinoma, and 100% chance that it's squamous cell carcinoma. And thus it displays its result right at the top. It also displays the image you just inputted right here on the left side. Most of the time, or oftentimes, we see that our model is very confident, in this case, 100%. But on occasion, we do see that our model errs. Very rarely, I'm glad to say. But in occasions like this, where this image is actually benign, in this case, our model is confused and predicts it as lung adenocarcinoma. However, on most occasions, our model is very confident that it is the right class. As we will see right here, with this image of lung adenocarcinoma, it's very close to 100% confident that it is lung adenocarcinoma. Now, to see our results on a larger test image set. So we tested this model on 3,000 images, and here are our results. So on the right side here, you can see a confusion matrix. And the objective of this is to maximize the diagonal from the top left to the bottom right. And so in this case, we want to make it as blue as possible. And clearly you can see we did a pretty good job of that. One big thing to note right here is whenever we predicted a benign, which is lung underscore N, on 0 cases were we wrong. So every single time you predicted benign, the tissue was actually benign. And this is particularly important because if a subject had actually had cancer, our model would not miss it and would not allow them to get to a later stage where they could be at greater risk. In line with that, whenever we predicted cancer, either lung adenocarcinoma or lung squamous cell carcinoma, on only 2 occasions was the tissue actually benign. And this is important to minimize because otherwise patients will have to undergo unnecessary treatment or incur unnecessary costs. On the flip side of things, our model was a little bit confused between lung adenocarcinoma and lung squamous cell carcinoma, as could be expected and shown on the bottom left and top right. But overall, we did a pretty exceptional job, and that's reflected in our scores here on the left side. The ROC AUC score of 0.9952 is meant to get as close to 1 as possible. And this signifies how well we predicted cancer versus our false positive, which means we predicted cancer when it wasn't actually there. So clearly we did a pretty good job there. And as far as misdiagnosed, only 2% of these images were misdiagnosed. And our confusion matrix score represents that, with only 70 images out of 3,000 misclassified.
In addition, we evaluated our model in 2 other ways with F1 score and accuracy. We were able to achieve a F1 score of 0.9766, which was very promising for us. To simplify, F1 score is a metric from 0 to 1, which is commonly used to evaluate machine learning models, where 1 means that our model always predicts correctly. Also, our model predicted correctly on the trained dataset images 99.7% of the time, and on the test dataset images 97.6% of the time. As we mentioned before, accurate diagnosis can drastically improve treatment outcomes, but it's sometimes hard for even pathologists to accurately differentiate between adenocarcinoma and squamous cell carcinoma. Therefore, we envision that when implemented correctly, our web application can help improve diagnostic accuracy and reduce time until diagnosis by providing accurate predictions. This in turn this computational approach, where an algorithm aids in diagnosis, will help doctors allocate their time to higher level decisions and difficult or rare cases. So in conclusion, our group has successfully developed a web application that can accurately diagnose 2 types of lung cancer. Thank you so much for coming to listen to our presentations. And before we take questions, we want to thank our instructors, Jordan, Jeff, and Thomas, our TAs, Emily, Charvel, and Ujjwal, and finally MIT Lincoln Labs for making these 4 weeks possible. We really couldn't have made it through without them. We also provided a link of our GitHub repository for our project on the slide.
Fantastic. Thank you very much, NASA Junior, for that presentation. Up next, before we conclude with some questions and answers to each of our groups, we have one more group to present, and that is COVE2D19. Are you guys ready to go? If so, feel free to start your screen share and take it away. Excellent. I can see that. Have at it.
Okay, so welcome to Image Classification of Chest X-rays for Diagnosis of COVID-19, brought to you by Group COVE2D19. So I'm Sasha.
I'm David.
I'm Andrew.
I'm Kaiji. And I'm Crystal.
Okay, so just to recap the problem that we're covering, the current used COVID test, which is a qPCR test, is both expensive and difficult to distribute. So diagnosing COVID using X-rays provides a cheaper, more reusable, and potentially more accessible option for diagnosis. Additionally, the current qPCR tests are associated with long waiting periods, which can be a serious issue when you're dealing with a highly contagious and potentially fatal disease. And they also have, unfortunately, higher rates of false negatives. Many other potential diseases, including bacterial pneumonia, viral pneumonia, and tuberculosis, can also present on lung x-rays, however, which makes it difficult for human doctors to recognize COVID-19 when it presents in the x-ray. So this presents the opportunity for a machine learning model to improve on this issue. Automatic x-ray detection with a machine learning model can provide faster testing, more accessible and cheaper testing, more accurate testing, and more efficiency for healthcare systems, since cheaper tests will lead to a higher availability of resources. So given all these potential benefits, there's a clear need for the development of a machine learning model which can accurately, consistently diagnose COVID-19.
We pulled images from multiple data sets on the machine learning website Kaggle. We pulled 6,324 training images and 1,970 test images. We put a sampling of these images on the slide right here. And without our labels to show that the image on the left was normal, the middle image was from COVID-19, and the right image was for tuberculosis, it's pretty likely that no one in the audience would be able to classify which is which. And when we built our model, we also had to consider the fact that our model might just be classifying random interference in these x-rays as COVID-19. So we added in control images from patients affected with the diseases of tuberculosis, bacterial pneumonia, and viral pneumonia to essentially ensure that our model was accurately predicting COVID-19 related pneumonia. The first model our group attempted was a convolutional neural network completely made from scratch. We used a litany, a big diverse variety of different types of layers to build it, but 3 stood out especially. The first was a convolutional 2D layer. Other groups have mentioned this. It's basically the meat of the model. It extracts features that essentially the model uses to classify the labels of the image. Secondly, we used a dropout layer to prevent overfitting, which is when the training accuracy is significantly higher than validation accuracy. Finally, we added in a batch normalization layer. These layers worked to essentially hasten the training time of the model, essentially leading to a better accuracy while reducing the amount of time to train. With all these layers, this does pose to increase accuracy, but also increase abstraction. Depending on the goal of this model, this could essentially create a model that is essentially harder to interpret, but also better at accuracy, better at classifying images. We used several different methods when fitting our model to our training data. One such method we used was early stopping, which essentially stopped training when the model is plateaued on an accuracy. We also, on a similar method, reduced the learning rate of the model to essentially prevent the model from essentially shooting past a high enough accuracy. And finally, we addressed imbalances using class weights, since our data was quite imbalanced. Here's some of the results from our from-scratch model. You can see that it's slightly suboptimal, because on the slide right here, our test accuracy was about 0.70, and that was about 10% lower than that of the model we went with. The other visuals represent the confusion matrix, represented in a precise numerical form as well as a visual form. The visual form, of course, is a little more interpretable, and you can see that it's slightly suboptimal because an optimal confusion matrix would have a dark red line stretching all the way from the top left to the bottom right. But here you see some shading in other areas, representing some areas of inaccuracy. We gauged our model on other different metrics as well. On the left, we tested testing and validation accuracy and loss. And since you can see that the blue and orange lines relatively converge, stuck together pretty accurately, we can tell that overfitting, like I mentioned before, didn't really happen. On the right is our multi-class receiver operating characteristic curve. The orange and purple lines represent classification accuracies for both tuberculosis cases and COVID-19 cases. Since they stretch towards the top left corner of the graph, this means that COVID-19 tuberculosis was classified pretty well. The rest of the curve stuck closer to the center, representing lower accuracies in terms of classifying these different labels, which is why eventually we decided to move on to a transfer learning model.
And so our second and final model used a model based on transfer learning. And to recap, this is a technique where an already trained and created model is repurposed for new applications, in this case, X-ray imagery. So we used the DenseNet 201 model with 201 layers that was already trained to pick up on unique characteristics from thousands of random images. You can see this on the right here. And the unique aspect about this model is that every single layer is connected to every single other layer, giving rise to many unique advantages. And furthermore, what these layers do is essentially extract the meaningful details from a photo, its defining attributes, and discards the meaningless data, the noise. And so what our model uses is first this transfer model, this DenseNet model, to extract those meaningful features, and then our own classification models to learn and predict whether an X-ray image is related to COVID-19 or not. So here you can see our results. And this model produced significantly improved results. For COVID X-ray scans, we had a 0% false negative rate on our test data. What that means is that out of 115 COVID X-rays, our model left not a single X-ray undetected and was further able to distinguish these COVID X-rays from other diseases that could be confused with COVID, like TB or other types of pneumonia. And for context, when the average patient begins showing COVID symptoms, the false negative rate for current tests is 38%. This means about 4 in 10 COVID patients are misdiagnosed in early stages. There's also a 92% true positive rate, meaning our model left very few false alarms. And this is really important because false alarms can put unnecessary strain on the healthcare sector. All in all, our model's F1 score, a metric of false negatives and false positives, is 0.96. Representing highly effective performance. And here are just 2 extra charts that represent the accuracy of the model. So on the left, you can see the ROC curve plotting the true positive rate against the false positive rate. The metric we use is called the area under the curve, where a value of 1 is perfect, and essentially is just a line shooting straight up and to the right. And so you can see the orange and blue lines represent normal and COVID X-ray classifications. And these lines are very close to an area under the curve of 1.0. Including all classes, the average area under the curve was 0.88. And so on the right, you can see a heat map, a different kind of representation of the confusion matrix. Again, this shows in that red rectangle that the COVID X-ray classification was highly accurate. However, you can see there in the middle area, the model had a bit of confusion for non-COVID related diseases, for example, mixing up bacterial and viral pneumonia. But keep in mind that the concern for our model, the primary and most urgent issue for our model is classifying COVID. And what our model does is classifying COVID X-rays highly effectively. And in addition, there are other ways to diagnose these other conditions like pneumonia and tuberculosis, but very few solutions for COVID.
So we have a demo video here of the web application we made, which uses the transfer learning model. There's an error, however. So you can upload an image of the patient's X-ray scan. It will run it through the neural network, and it will output the probability of the patient having each of the diseases. The shown in this slide are the results returned when we ran X-ray scans of a patient with healthy lungs and of a patient with COVID. When we input the normal X-ray scan, the model predicted that the probability of the patient having normal lungs is 95%, and the probability of other diseases are all quite low. When we input the COVID X-ray scan, it predicted that the probability of the patient having normal lungs is 12%, whereas for COVID, it is 87%. So using these predictions, it successfully determined that the patient indeed has COVID.
So all in all, our transfer learning model's accuracy in identifying COVID-19 infected lungs shows that it certainly has potential applications in the medical field. But besides its accuracy, what exactly are its strengths? Well, using our web app, the model can predict the classification of a single X-ray in less than 30 seconds, as well as provide a probability for the scan belonging to another class. This is convenient and also a really crucial time saver for doctors who need to quickly determine a patient's status, or maybe in a scenario where the pros and cons of a treatment need to be weighed before it's actually administered. So the model is also far more accessible than traditional means of diagnosis, as it only requires a computer and an internet connection once you have a scan, and that's opposed to a potentially expensive and lengthy qPCR assay. Our hope is that our machine learning model may make some contribution, however small, to the chaotic world of COVID diagnosis, potentially easing the burden on doctors and healthcare workers across the country as they try to keep up with the new pace of cases. And more broadly, our transfer learning model's ability to produce accurate results with only a few days of development is indicative of a future in which machine learning, with the aid of medical data like X-rays, but even electrocardiograms, CT scans, and more, could greatly improve human doctors' ability to diagnose disease. So in the way of data, Like other groups, the data to make this project was found on Kaggle, and though we have quite a number of them here, spanning tuberculosis to pneumonia to pediatric scans too, we ensured that each one had equal representation across the training, validation, and test sets for a model. And so finally, I'd like to thank all of you for tuning into our presentation. And of course, I want to extend a huge thank you to the Beaver Works Summer Institute, our instructors, teaching assistants, who dedicated so much of their time to work tirelessly with us and teaching us how to make machines learn and make our coding dreams come true. So thank you.
Fantastic. Thank you so much, Cove2D19, for that. All right, well, we have just a minute or two before we can transition to the question and answers. And I just wanted to take a moment to say, first of all, who am I? I'm Jordan Montgomery. I'm an employee at Lincoln Laboratory. I apologize I didn't get those introductions in right off the bat for this session. We just wanted to make sure the students had plenty of time to do their presentations. But I've had the honor and privilege of leading the Medlytics course this year, alongside two excellent co-instructors, Jeffrey Arena and Thomas Curtis. And we've had a stellar staff of teaching assistants as well in Emily and Charvel and Ujwal. So kudos to all of you for all of the hours that you've put in to make this course a success. And I think, as you can all see, all of our students have really benefited a lot from that and learned a lot from all of your efforts. So thank you for that. But with that, I'm going to hand it over to Jeff in order to serve as MC for a few questions that have come up during the course of your presentations.
Thanks so much, Jordan. Yeah, so I've been trying to go through and look through some of the questions that have been asked during the presentations. I'm going to try to ask them in the order that the groups presented in. So I'll start with FatiQue and Slept, and we'll try and see how many questions we can get through in this 20-minute period here. So if I can get FatiQue and Slept ready to answer some questions. I have maybe two or three to lead us off with. We'll see how long those take. So hopefully representatives are standing by. First question, did you attempt to create any of your own networks before you utilized transfer learning?
So we did not create our own neural network architectures, and this is because the pre-built models are trained on datasets with millions of image samples and are therefore much more equipped for classification than custom-built models. So this is a commonly used tactic in image classification, as almost every single professionally created model utilizes transfer learning. Pre-trained models are the industry standard, and that is why we chose to use them.
All right, that makes sense. Thanks for that. A second question, also coming from that Q&A chat. Why did you not include more people in your validation and test cases? I guess it's a question about why you chose the particular values for validation and test set sizes.
I can answer this one. We chose a relatively low amount of validation and test set samples because in general, they're useful for detecting overfitting, but a larger training set is more effective at preventing overfitting. And additionally, to clarify, the main problem with our process was the imbalance of data, not overfitting. And we countered that by using class weights, by using different loss functions, and etc.
Interesting. Yeah, and I noticed too, you were one of the only groups to use k-fold validation. Another method to reduce overfitting, which makes total sense. Let's see, we have 5 groups to go through. Yep, we have a little bit more time. Let's see, some folks were asking about precision statistics for the model. I'm not sure if you had that question or if you had those numbers offhand. If you happen to have them, that's okay. If not.
Yeah, it's okay. I can take that question.
Cool.
It's a good question, by the way. Just for clarification, the custom metric that we were talking about that Kaggle is using is called the receiving operation metric in area under the curve, the ROC, AUC that everybody else has been talking about as well. For those of you who don't know, it's essentially a modified accuracy for a binary classification. So as we discussed, the AUC ROC is 0.94, which is significantly higher than what we achieved the first week of 85%. So, happy linings. And going off previous models, speakers, and lectures we attended, our group found that accuracy is a stronger metric, especially because we want to make sure that we're making new images in the right categorizations rather than having the same image get the same result every single time. That just has more real-world applications, and it's probably more applicable in the medical field. So given that our AU-ROC is in the 90s, I'd also imagine that our precision, recall, and specificity would also be quite high. But definitely moving forward, we're going to take into account more statistical analysis, more precisions. But like Sion said earlier, a big issue with why our AU-ROC is slightly lower than our accuracy is because of our data set. To specify, we have 98% benign cases and 2% malignant cases. It's definitely more precise than what we could have with less data or biased selection. But we don't really want to touch that sample because then that becomes slightly unethical on choosing who is and who isn't qualified to be used in training. So,
oh, sorry.
Yeah. Sorry, I was just going to wrap it up and say that moving forward, we're definitely looking into finding more data, stratifying our results, so on as the competition nears its end.
Thank you so much, Clarice. And yeah, one thing that's great about your group is that you're continuing to develop your model for that calc competition, which is fantastic. Moving on to Rona group, the second group to present. One question was about comorbidities, so other risk factors that may have played a role in the level of risk for COVID, besides that which you were detecting. Did your data have any characteristics that allowed you to control for comorbidities, or was there any thought into trying to control for that?
Yeah, so I can answer this one. So because we were trying to train on patient data, there's a lot of regulations like HIPAA protecting privacy, and that's why we actually had to get our data set. It was a Mexican data set. So I think that we kind of hoped at the beginning of our project to find a more comprehensive data set that had more symptoms, but because of all the privacy concerns and because it's such a new disease, this was the best we could find that had individualized patient data and had some like outcomes.
Okay, that makes sense. Yeah, data availability is definitely a big concern overall in machine learning. Another question was just, could you clarify which models you actually used to generate your classifiers, what types they were, maybe what decisions you made to arrive at those models, yeah.
So if you're specifically in our presentation, we talked about how we use a decision tree, which is basically like it like starts with a root and then it goes into a bunch of nodes. We have a more detailed explanation in our video, but Rachel went over basically what it was. And to make our model more consistent, we use a random forest generator, which basically has like 50 or something of these decision trees. And in the end, they just look at the results from those 50 decision trees and do just majority voting to determine which classification each patient will be put into. We did try a few other models. For example, we tried SVM models, and we also tried KNN models, but because of the binary nature of so much of the data, we decided that a decision tree would probably get us the best results. And that is, in fact, what happened.
All right, I think we might have time for one more. There was a question on basically how you arrived at which variables to consider for your classification model. If there was a method by which you arrived at those attributes to hand to your classifier.
I can answer this one. A lot of it was like guesswork, kind of. We also did a lot of research like on like backgrounds of COVID-19 and how like various conditions would affect the like the patient's like complications. So like, for example, age was actually one of our classifying features, simply because older people are like more susceptible to having complications due to COVID specifically.
Okay. All right, thank you. Thank you, Avery. I'm gonna keep moving because we need to get to the next group. Thank you so much, Rona Group 1. Next is Neuro Bureau. First question, did you consider using any multi-imaging modality approaches, pulling in other sources of imagers like PET, CTs, or MRIs for Alzheimer diagnosis?
So we did not, because we were limited by our data set, which only had MRIs. But if we were to incorporate those, it shouldn't be too hard. And that also seems to be related to the second question about whether our model can adapt to other clinical parameters, such as MMSE scores and education levels. So our plan is in the future to add in, maybe write a different model to add in different features to help with classifying the different stages of dementia related to Alzheimer's.
Okay, thank you, Jerry. Thank you for getting ahead of me and finding the questions in the chat for your group. That's awesome. There was another question, which you probably saw as well, asking about which optimizer you used for your network and what experience you had configuring the hyperparameters for your network optimizer.
Well, for LINET 5, we used Atom as the optimizer, and we used a learning rate of 0.001 and 100 epochs, which is basically one pass of the dataset through the model. And these hyperparameters were mainly chosen through trial and error, so this combination resulted in the highest model accuracy.
Okay, yeah, no, I know there was definitely a lot of required learning on the learning process that had to take place in all the groups during the optimization. Let me see if I have any more questions for Neuro Bureau. Really interesting question. How might you prevent a patient from worrying if they have Alzheimer's if they upload a picture of their brain scan?
So to answer this question, our app is a tool that clinicians can use in addition to the results of other diagnostic testing, such as cognitive tests, analyzing a patient's medical history. So our app is not a substitute for Alzheimer's diagnosis, but the results should be taken in conjunction to aid the clinician in forming a diagnosis.
All right, good answer. Thank you. I'm going to keep moving because we have a hard stop right at 2:20. Thank you very much, Neuro Bureau. Moving on to NASA Junior. There was a good question about comorbidities again. Basically, was there any way for you to use your data to figure out if the symptoms you were observing were purely due to lung cancer and not other comorbidities like viral infections?
So I can take this one. So although we did not specifically look for any comorbidities aside from lung cancer specifically, I'd like to say that we're confident that it is explicitly due to lung cancer because we used CNN and transfer learning like we explained before. And so the training set we used, our model is designed to pick up on specifically lung cancer tissue. And so the benign tissue in the training set may or may not have other comorbidities, we're not sure. But yeah, so although we didn't specifically look to identify those, we feel like since we trained on that big data set, our model understands which is lung cancer and what's not. And as seen by our results, we're pretty confident that it worked out. But yeah, that will be something to look into in the future as well. So great question.
Right. Good answer, Neil. Just a question, another one. Concerning the resolution of your images, so there was some concern about potentially losing emerging granulomas in the model by choosing a resolution that may be too coarse. I'm sure you had plenty of consideration over exactly how high resolution you went with in your final model, understanding all the computational constraints you were under. Can you speak a little bit to how you chose what resolution you did for that model?
Yeah. So we were initially also worried that we'd lose the details in the images by resizing them, but we remembered from an earlier challenge that which was detecting cancer from mammogram images. We resized to about 150 by 150 pixels, and that could detect the machine learning models could detect the tumors as cancerous very well. So we decided that we could resize these histopathological images as well. And to take into account of the zoom, to take into account of the resize, we use the zoom features, the zoom data augmentation. And we specifically resized to 224 by 224 because of the transfer learning model we used, which was VGG19, which took images that were 224 by 224.
Just to clarify, Akshaya, when you say you went down to 224 by 224, were you subsampling the original larger images or actually changing their resolution?
We were changing their resolution.
Oh, okay. Very good. I think we might have one more question opportunity for NASA Junior. How do you account for lung cancers your model could not classify, like other types that may not have been in your set of classes?
Yeah, I can answer this question. So the reason why we focused on adenocarcinoma and squamous cell carcinoma was because they're the most common types of lung cancer, and they account for more than, I believe, 80 to 85% of all lung cancers. So our primary focus was on this first, and then in maybe later models, we can focus on more different subtypes of lung cancer that are not as common as adenocarcinoma and squamous cell carcinoma.
All right, that makes sense. So you started with most popular cancer
Yeah.
types, or most common cancer types more
Yeah,
accurately.
and I'd like to add, actually, if I may, that our model did train on benign versus these two other types. So I feel like if we did get other cancer types, our model would probably still be able to identify that it was cancer tissue, if not exactly what class it was in. As you saw before, we never mispredicted a cancer tissue. If it was those cancer, we knew it was some sort of cancer. So we're pretty confident that other types as well would achieve similar results. But yeah, that's something to look into for the future.
Very good. Yeah, no, I remember that attribute of your model not having any false negatives, which is definitely a great attribute for a cancer classification machine learning model. So moving on, finally to COV2D19. First off, did you folks consider any chest CT or MRI images? I know you did a lot of work curating your data set from multiple Kaggle sources. Did you consider things other than X-rays?
I can, I guess, speak for the group. We did heavily consider CT scans, except we did not find like a significant amount of CT scans to essentially provide for a model that we could really compare to the X-ray model. So for the sake of time and for the sake of the quality of our final work, we decided to focus on X-rays primarily.
Yeah, I know data availability is probably a huge driver for machine learning model development, so that makes total sense. Another question, maybe a little bit one step beyond machine learning, but I'll pose it out to you guys. X-rays are more expensive than COVID tests. How would you convince patients to spend more money on X-rays instead of maybe a less costly PCR test? This is more like a policy question, so it's a little bit out of the scope, but yeah, take a whack at it.
Well, for this one, I'd say that having a test is better than having no test at all. And especially for COVID, it's not just a question of price, it's also a question of availability. And for the other two options, at least, like CT scans, well, I believe there are only 41 CT scanners per 1 million people in the United States. So that's a question of like, do we even have enough to support the number of tests we need? And also for like lab tests, there's a significant turnaround time. So even if the price is a little bit higher, I think in certain cases it takes priority to get the test result out faster. And that would be the case with X-rays.
Interesting. Really, really good points. I think that was the last of the questions for COV2D19. If any TAs or instructors on the channel want to pose their own questions, they can feel free. Otherwise, we don't have a ton of time. I just want to thank all the students and co-instructors for their time. I really, really enjoyed it. There were a fair amount of late nights, but I think we all benefit now from that experience.
So Jeff, there were actually a couple other questions in the Q&A list for COV2D19.
Oh, I'm sorry. Maybe I'm not updating. I only see.
I think there were.
Feel free to parrot them out. I didn't see them.
One of them has disappeared, so maybe that question was redacted. I thought I saw one, but there is one.
Oh, I see what you're saying. Okay, so there was a question about this other paper, Thomas. Is that?
I think the question that I was looking at has been redacted, but that question does exist as well.
Well, so right, this one, it's sort of like, have you heard of this in your research? There was a paper published in the Journal of Cell, maybe Cellular Biology, already that ran an ML model on chest X-rays to diagnose COVID-19. Do you know how your model compared with that model?
So I'm not familiar with this particular study in the Cell Journal, but I have read a bunch of other studies and papers that used machine learning to classify COVID-19 based on radiological images. And so something I noticed is, and some advantages our model has is, one, our model has more controls. So most papers only have viral pneumonia as like another control. So they have classified healthy lungs, COVID-19, and viral pneumonia. However, our model includes both all three: viral pneumonia, bacterial pneumonia, and tuberculosis. So we think that makes our model more robust for distinguishing COVID from other diseases, especially because COVID has very non-specific symptoms, and that's like a big problem in the healthcare sector. And secondly, data set size. So we compile data from numerous different sources. And so from what I've observed, we have a larger data set than most published papers, and B, data from numerous sources and machines like all around the world. And this means that like they have like different resolutions and qualities, which our model is able to account for and also provide a better generalization. And like in terms of results, I think our model performed on par or better than most papers. So as I've mentioned, we achieved a 0% false negative rate, which is the most important accuracy metric for our model, and an overall F1 score of 0.96.
Thank you very much, Andrew. I have to cut you off a little bit because we have 30 seconds before I think we're going to be hitting a hard stop, but great answers. Thanks for taking the time. If any other instructors want to say anything in the remaining 20 seconds, if not, thank you everyone for your time, and thank you for those tuning in. Really enjoy this whole process.
I will jump in very quickly just to say, students, I'm going to be sending you a link through Discord to get back to that main area for the closing ceremonies. And those watching through the webinar, if you click on the link at the very top of this page that looks like a beaver, that'll also take you back to the main area for the final closing ceremonies. Thank you so much for joining us today, and take care.